Let's look at interconnection topologies. Interconnection topologies are set up with a set of inputs and a set of outputs. Let's say there are n inputs and m outputs. The inputs need to be routed to the outputs by a set of control signals. So control signals, there may be a single control signal if it's a 2x2 switch. If it's a larger switch, you need more control signals. They determine how the inputs are routed to the outputs. Usually we'll assume that there is the same number of inputs as there are outputs. Now let's look at a set of different interconnection networks, starting with a ring. Ring is very simple. Each processor, or each node, let's say, is connected to adjacent nodes, I plus 1 mod n and I minus 1 mod n. You can get data from anywhere to anywhere else in the network by a sequence of cyclic shifts, means end-around shifts where the last processor or last node's data gets routed to the first processor or first nodes. The motivation for that is that a lot of parallel algorithms average two adjacent elements to determine the new value of one element. Usually every item except the first and the last is updated in that way. The first and the last one may be masked off so that they don't get updated at all, for example, if there are boundary conditions. And this is similar to the 4-point iteration we saw earlier in this course, except it's only in one dimension, not in two dimensions. The processor interconnections can be diagrammed as a bidirectional ring. Now let's take a look and determine what are the metrics for a bidirectional ring. The second kind of interconnection we want to look at is a mesh. This is a two-dimensional mesh as we show it, but actually it could be more than a two-dimensional mesh. You have higher dimensional meshes too. A mesh is like having row and column cyclic shifts. In other words, you can cyclic shift an element from one end of a column to another, and similarly you can shift it from one end of a row to another, although in this particular structure called an iliac 4 mesh, instead of going directly around the same row, it goes on to the next row, and ditto, G goes to G, H goes to H, and E goes around back up to H. So you have a single cycle in one dimension, the horizontal dimension, and a set of cycles in another dimension, the vertical dimension. Now the motivation for this is 4-point iteration, which I alluded to a moment ago. Here you take the average of the 4 elements surrounding a particular element and assign that as the new value of the element. And those calculations are frequent enough that interconnection networks have been designed to perform them efficiently. In the iliac 4, which was the first processor or first multiprocessor to use this kind of interconnection, iliac 4 dates from, I think it's 1972, long time ago. Each processor was connected to processors I plus 1 and I minus 1. You can see that right here, you know. 3 is connected to 2 and end around 3 is connected to 4. And it was also connected to processors I plus 8 and I minus 8. And here, for example, this one is connected to processors I plus 4 and I minus 4. And that's because we're showing a 16-element mesh instead of a 64-element mesh. The iliac 4 used a 64-element mesh. The diameter of a mesh is the square root of n minus 1, and I think you can see that here. You know that the farthest you can go is square root of 16 is 4. 4 minus 1. You can only go 3 in any particular dimension. For example, in a 16-node mesh structure, it takes a maximum of 3 steps. Now, actually, it's not really that simple, but if you show the, you know, what I was alluding to here is that you only have 3 connections in a particular direction. But that's not really the right way of looking at it. The right way of looking at it is along with the end-around connections. So let's say over here, as you can see, node 3 is connected to node 4 and 2, but it's also connected to 15 and 7. And so you see here 3 is connected to 7 and 3 is connected to 15. Now if you draw the iliac for a mesh like this, it's fairly easy to see that the diameter is 3. So let's take, for example, nodes that don't seem to be related very closely at all, like let's say 1 and 6. Well, there's a 2 hop path from 1 to 6, 1 to 5, and 1 to 6. If you take 1 and 10, then what I do is go from 1 to 13, and 13 to 9, and 9 to 10. And if I wanted to look at the distance between 0 and 6, for example, I'd go 0 to 4, 4 to 5, 4 to 6, 0 to 7, go 0 to 4, 4 to 8, and then 8 back to 7. And I think you can see that there are no two nodes that are greater distance apart than 3. In a 64 element mesh, any node can be reached from any other in no more than 7 of these shifts. And that's because, you know, if you had a 64 node mesh, you've got a much larger structure, but instead of 3 hops, you might have as many as 7 hops. If you didn't have the end-around connections over here, so if you didn't have G go into G and H go into H and so forth, then the diameter would be 2 times the square root of n minus 1. And that can be seen pretty easily here. The worst case is from 0 to 15. If you don't have any of the end-around connections, you bop 3 nodes across in this dimension and then 3 nodes down in that dimension, and your total distance is 2 times 3, or 6, which is indeed 2 times the square root of n, which is 4, minus 1. It's also possible to have a multidimensional mesh, as I mentioned a moment ago. The diameter of a multidimensional mesh is d times the dth root of n minus 1. And I think you can see that in the same way. You know, if you have a two-dimensional mesh, the diameter is 2 times the square root of n minus 1, as we've just seen, and that generalizes to higher dimensions as well. And the bisection bandwidth is n to the d minus 1 over d, and I won't bother to show you why that is. The average distance is d times 2 times the dth root of n divided by 3. That is without end-around connections. That's what we're talking about when we use this formula right here. No end-around connections. Okay, so those are 2 interconnection structures. The mesh interconnection structure is very common today, and rings are used too, but mostly in local area networks rather than multiprocessors.